to make a correction. Because this is wrong. All right. Wrong. I need to correct it. I'm glad 2 students pointed it out. So actually, based on our original question, we do not count unit squares actually. Yes, not unit squares. So we count the number of squares of certain sizes. All right. So the first such square with even number of unit squares, only one. Okay, only one, or 1 square. Then the second size, 6 by 6, 3 square. Invariant, remember invariant. 8 plus 1 invariant. 8 plus 1 equals 9 invariant. 6 plus 3 also equals 9 invariant. Okay, 4 times 4, 5 square invariant. So 2 times 2, 7 square. So we should calculate correct way, 1 square plus 3 square plus 5 square plus 7 square. 1 plus 9 plus 25 plus 49. Okay, 84. 84 is correct. Okay, this is wrong. Okay, this is wrong. All right. I got confused. I got confused. All right. So we change based on the correct understanding. Okay. So let's continue. Next question. So this one, counting by reference. Now it is very easy. So we take the subscript or superscript. Subscript, superscript. 5 equals 3 times 1 plus 2. The remainder is 2, 3 multiple plus the same remainder. Okay. So now the last one, 302, 3 times 100 plus remainder 2. So now we can use these numbers, 1 to consecutive numbers, as our counting objects. So we count these numbers. So 100. Okay. All right. So number 17, the answer is 2. The answer is 2. But I noticed one problem. When I grade one problem, so some student may use this method. Okay, some student, they create some special examples. Some students just right example. Then they count how many elements not in place. Then use that counting number as the answer. So that student count 3. In that example, it's 3. But your example may not be the best. Okay. We want to find the best one. Okay. The best one. All right. So the thinking is like this. Unordered. First, we know unordered. Unordered tell us K cannot be 0. K must be greater than 0. If K equals 0, then no inversion, right? So the logic is if K equals 0, that means no inversion. 0 inversion, so no inversion. No inversion means array is ordered. No inversion, it's ordered. Ordered, that's a contradiction. Because we're given ordered array. So you get all contradiction. You get contradiction, that means this condition is wrong. So K must be greater than 0. Yeah. All right. If greater than 0, is it possible K equals 1? Yeah. You need to think about it. Possible K equals 1. Yeah. That is, given an array, only one element is not in place. The remaining n-1 are all in place. That's impossible. If you get the remaining n-1 all in place, the last one must be in place. Only one position left. That position must be the correct one. Yeah. So this tells us impossible. Okay. Not possible. Okay. It's not. So 1 is not possible. Then the next number you need to consider is 2, but you also need to make sure 2 is achievable. You can get 2. Is it possible to get 2 elements not in place? Achievable. Yeah. That's easy. Think of so you start with, yeah. Think about it. You start with an ordered array. You start with ordered array. Then swap 2 elements. Then those 2 swap it, they are not in place. In that case, K equals 2. In that way, you complete the whole procedure of the solution. So the last step, make sure your answer is correct, achievable. That 2, you can get that 2 number. You need to find an example. Otherwise, 2 may not be achievable, right? You need to consider 3 if 2 not achievable, okay? And so on. Yeah. All right, yeah. Number 18, although find the median, the answer is 3. And we know sort a 3-element array we need 3 comparisons. Okay, yeah. Here, finding the median, for the worst case, you cannot use 2. If you do 2 comparisons, for the worst case, you cannot find the median. Then, if you use 3 comparisons, you already get it sorted. Then the one in the middle, that is the median. Yeah. Yeah. So this 3-element case is a special case. Yeah. Because in the general case, general n-element array, usually when you find a median, you do not need to sort the whole array. You can find a median without sorting. Okay, think about this. If you do sorting, you do more than you need. You do some extra work. You do extra work. You do extra work. Okay, yeah. Here, let me tell you the general result. For sorting, the general case, remember, yeah, I mentioned that the best algorithm we have for sorting n log n. Okay, n log n. The worst case, average case, n log n. Okay, sorting. For the median, we haven't learned the best algorithm is big theta of n. There is no that log n. Okay? Big theta of n. You can find the median. That means you do not need to do that much work, sort the whole array. Okay? You can do less work to find the median. You do not need to sort the whole array. You only need to do sufficient work to get to know that some element is the median. Okay, for example, yeah, so here you may feel a little hard to understand. Yeah. All right. It could be like this, for example, it could be like this. For example, to find a median of 5 elements, median of 5 elements. Here, I want to explain why you do not need to sort. Okay, find the median of 5 elements. Yeah. After you do some comparisons, you notice some element is among top 2. After a certain number of comparisons, you find some element is among top 2, then you can eliminate it. So, but the top 2, it is the first one, the second one, it doesn't matter. Because we don't want to know it. First one, second one. It's not important. We just eliminate it, right? After you eliminate, you don't know it's top 1 or top 2. It's the first one or second one, okay? That means after you find a median, you do not know which one is the first one, which one is second one. So you don't know that, but you can find the median, okay? So that tells you, you do not have to do sorting to find the median, okay? You can do less work than sorting to find the median. Yeah. Because some unnecessary information, you do not need to know. Which one is the first one, which one is second one? That information you do not need to know. Okay, so you can save some comparisons. Yeah, yes, that's just example. Okay, yeah. So you can see here why the median, we just need a big theta of n. Know that log n. Yeah. All right. So here, yeah. Yeah, so this question, definitely, I think you can use, you know the details, find the median with 3 comparisons. Yeah, so here, I do not put the details here. Yeah. But I did a sorting one in our review. Okay, review 1. Review session number 1, I sort 3 elements. Yeah. So that one, you can use that same way to find the median. Yeah. All right. Yeah. But starting, yeah. So here, this when n greater than 3, then the number of comparisons to find the median. Yeah. So let me write the number of comparisons to find the median. Let me write number n. Okay, will be strictly then the number of comparisons to sort. Okay, won't be equal. Okay, yeah. Yeah. All right. Yeah, but another thing for the median, when you have even number of elements, what is the median? So for odd, you know the one in the middle, right? Yeah. So this, when you have even number of elements, we need to find a median. Okay, yeah, okay, yeah. In this case, there are 2 elements in the middle, similar situation in the middle. Yeah. Okay, the one at the left, we call the left median. The one at the right, we call the right median. okay? But the left median is the default median, okay? All right, so that's our assumption. The left median is the default median, okay? Yeah, it's certain, yeah, because later when people ask you to find the median of an array with even number of elements, the definition is clear, left median, okay? Yeah, because some students may ask, which one you mean? Okay, which one you mean? Yeah, left or right? Yeah, but here I like to let you know the meaning of median. So when you read different books, it could be different. Okay, yeah, because in some, you know, middle school math books, so they have another different definition. They use the left median plus the right median adding up divided by 2. They call this method. Okay, we don't use that. Yeah, because the reason, if you use that, this number won't be any element in the array, right? Median, we mean it must be some element in the array. It cannot be element out of this array. Yeah, so that's why we don't like this definition. Okay, so we do not get confused. Okay, so all right. Next question. Yeah, number 19. Yeah, number 19. Answer is 4. So actually, in my hands, I pretty much gave you the solution. You just complete it. Okay. Yeah, I give you a lot of information. Just last step. Okay. Yeah. So here I do not repeat it. Okay. I just, you know, work on some other elements. Yeah. So here, number 20, the answer 180. Yeah, actually n minus 5. Yeah, but I need to explain this one a little more. Yeah, because some students put the number here by analogy, not by logical reasoning, right? By analogy. Yeah, analogy, because our finding the minimum, that is n minus 1 answer, right? Yeah, but here finding top 5, top 1. Yeah, so here the analogy is like this. Top 1, our answer is n minus 1, right? Then by analogy, top 5, the answer is n minus 5. Okay, yeah. Yeah. Some students did in that way. Yeah. But here I want to give you, you know, the whole solution. Yeah. Because by analogy, that's not solution, right? That's not solution. Okay, yeah. No logic reasoning behind it. Okay, because people may ask, oh, why you can't apply this analogy? Why? You need to justify it. Okay, yeah. Here, let me give you the justification. The justification, very simple, still by the elimination method. Elimination method. Yeah. Yeah. When I erase something, it's very slow. Elimination method. Okay. All right. The question is how to apply. Yeah. The hard part is how to apply. You need to set up. Okay. Yeah. You need to arrange your data in a well-organized way. Then you can apply elimination method. Now that part, the setup, that part is hard. So let's do that part. Okay. All right. So our goal, we want to eliminate certain number of elements. That number we know, okay? Yeah, so our goal. So here, let me put the goal. How to get top 5? Yeah, so we interpret our our top 5 go in another different way. Okay, top 5. We know our goal is top 5, but we write it in differently. To get an element in top 5, we need to eliminate (180) elements. Okay, we need to eliminate 180 elements. Then only 5 elements left. Top 5 elements. All right, so eliminate 180 elements. That means we find one element that's greater than 180 elements. Okay, so here we do another step forward translation, another step forward. Okay, find an element that is greater than 180 elements. Okay, yeah. Yeah, because in that way, we can treat as elimination that particular one that is greater than 180 elements, that one can eliminate those 180 elements. That one is definitely greater than 180 elements, so that one must be among top 5. Think about that. Okay, all right. The next question is how to get one element that is greater than 180. So that's simple. How? So here, because we want to do the easiest way to get that element. How? Okay. Yes. So how? Just select. Okay. Writing is so slow. Select arbitrary. Let me. Yeah, I feel probably my computer memory problem. When I reach some point, writing is so slow. All right, select. Let me just write any. Okay, yeah, any 181 elements. Okay. Yeah. Any, and find the largest one. Find the largest one. Yeah, it's the largest. Next time when I it looks like, yeah, so bad. One element. All right, yeah, the largest. Okay, largest one. Okay, that's the one we need because the 181, the largest one, it is greater than the remaining 180. That must be among the top. Okay, yeah. That's important. Okay, yeah. So we get it. So you know all the details for the solution, not just by analogy. Okay, yeah. n-5 by analogy, that's not enough, not good enough. Okay, yeah. All right. So after you know the details like this, all the things, then if I modify this question to a different version, yeah, so you can use the same way thinking to find your answer. Otherwise, when I do the modification, then you cannot apply analogy anymore, right? Yeah, because I add extra condition. No analogy could be used. Okay. Yeah. Don't have extra condition. But in the real world, where you have a real computing problem, you cannot ask, right? If your customer requires certain condition, then you cannot say, oh, remove that condition. You cannot say that, right? Yeah.
But generally, solve it the first time, you probably.
Yes, yeah, you got it. Yeah. So actually, yeah, that's a good problem solving method. Good problem solving method. All right, so let's move to the next one. Yeah, next one, in my hand, I did a lot of analysis. Here, I want to do the continuation. I don't want to repeat the same analysis. That's too long. Okay, so here, let me just complete the second half for the solution, for the answer. The answer 2n-3. The formula 2n-3. Okay, yeah. Here, let me give you the answer, that step. Based our analysis in the hand, we know these two elements to be swapped should be the first one and the last one. Yeah, let's write A1 and AN. Because in this way, we can get maximum number of inversion change. If not the first one, last one, then you won't get the maximum. You can still push these two elements to two ends to get a more number of inversions. Yeah, so here we assume that. Okay, all right. So we will swap these two elements to get a maximum number of inversions. Okay, yeah. So let's assume A2, A3. All right. So in the middle, all those other elements in the middle, -1. Okay, yeah. Yeah. Now, so for the answer, yeah. Annoying. Yeah. I think the memory is important here. Here I only have 4 gigabytes. Yeah. So the next time when I change a computer, I need a larger memory. All right. Yeah. So that probably not that important. Yeah. Yeah. Well. All right. All right, yeah. So how about we assume A1 is the minimum minimum, and AN is the maximum. To get the largest number of inversion. All right. Now, after the swap, AN becomes the first one. AN, and A1 becomes the last one. Okay. Yeah. Now, let's think in this way. Yeah. Let's look at the contribution of the inversions from A1, AN. Okay. Before we do swap, AN does not provide any contribution to the inversion, right? The largest one at the end, no contribution for the inversion. AN. Okay. Yeah. Before the swap, A1 does not provide any contribution to the inversion. A1 smallest at the first one, no contribution to the inversion. So before swap, both A1, AN do not provide any inversion. Okay. After the swap, AN provides the maximum number inversion. Yeah, because you take AN with any other elements, you will have one inversion. So AN, after the swap, it will provide N minus 1 inversions, added inversions. Okay, think about this is added inversions. Okay, added. All right, yeah. Then A1 similar to AN, all right, but there is one inversion between AN and A1 that must be excluded. Yeah, you already counted. AN, A1, you already counted. In these N minus 1 added inversions, you already count that AN, A1. Okay, so the next time when you count number of inversions with A1 involved, you should not look at the AN anymore. Okay, yeah, only look at A1 with other remaining elements. Other remaining elements, there are N minus 2 other remaining elements. Okay, so this N minus 2, that is the added inversion. Okay, so then you added these two, N minus 1 plus N minus 2. So your answer is 2N minus 3. Okay, that's how we get the answer. Okay, yeah, A1, AN. The extremal cases. Here we look at the extremal cases. Yeah. But when you count, do not count the same inversion more than once. Be careful on that. So then, yeah, okay. All right. Yeah. So the next question, number 22. Number 22, solution. Yeah. So just remind you, when you see the solution, you need to provide some more information to get the answer. I do not need you to write a lot of words. Just let me see you get the answer correctly. Just convince me it's not your guess. Yeah. If I see you put answer there, that's your guess. Then it's not good enough. You need to convince me you have the logic to find the answer. Okay, you have the critical logic to find the answer. That's good enough. All right, so here, A1 less than A2 less than A3. Yeah, but yeah, and the B1 less than B2 less than B3. Also, we know A2 less than B2. Okay, yeah. Here, now, the third smallest. Yeah, so now we need to use some idea I talked about before, all right? The median, third smallest. That's we look at from left-hand side, right? Left direction. There, yeah, so here, this is the one, okay? From the right direction, it is the fourth largest. Okay, yeah, same element, yeah, but when you look at from different directions, that rank number is different. Here we call the rank, okay, yeah. This third, 3, we call the rank is 3, rank 3. All right. All right. We consider from both directions, then we can eliminate as many as possible. If you only consider one side, you may not catch all the qualified elements. You may miss some of the elements, not all the qualified elements. Okay, all right, yeah. So now, when you look at from one side, yes, here. Yeah. Let's look at A1. Yeah. A1, we know A1 is less than how many elements we want to see. Okay, A1, we know it's less than A2 and less than A3. Also B2, right? Because B2 is greater than A2. A1 also less than B2 and B3. Now you can see A1 is less than at least 4 elements. A1 is less than at least 4 elements. Okay, yeah. Look at the fourth largest. The median is fourth largest. So this tells us A1 cannot be fourth largest. Okay, A1 cannot be fourth largest. So A1 can be eliminated. All right, yeah. It cannot be the fourth largest. All right, so then third smallest. Let's look at the third smallest. Okay, B2 and the B3 greater than A1, A2, B1. Right? Yeah. B2, B3 greater than B1, given condition. B2, we know B2 greater than A2. So A2, A1 less than A2. So B2, B3 should be greater than A1. Yeah. All right. So they are greater than at least 3 elements. Okay. So this tells us B1, sorry, not B1, B2, B3. Okay. Yeah. B2, B3 cannot be third smallest. Right? Yeah. Because you already find at least 3 elements smaller than these 2, cannot be the third smallest. Okay. Yeah. So the answer, yeah, answer, these 3 elements can be eliminated. A1, B2, B3 can be eliminated. Yeah. Yeah. That's the information I want to see, so that you can convince me you have the solution. You have the logic for the solution. All right? Yeah. look at from two directions. How many elements greater, smaller than our, target element from two directions? Yeah, this way. Okay. Yeah. All right. Number 23, two methods you can use. One, you use the limit method. N goes to infinity. You take the limit. You're allowed to do that. Yeah. Here, because I do not say you cannot use the limit method. Okay. Yeah. And this way, six, or yeah, denominator. Yeah. All right. N. Okay, denominator N. All right. Then answer is 1. If the limit is constant, so your conclusion, you have that conclusion. Okay, that's enough. The limit. Okay, all right. Then the second one, then you need to use inequality. Inequality, yeah. In our examples, I said, yeah, you need to consider inequality before that 6th power. Then you raise to 6th power. Okay, yeah. So n less than n plus 4 less than or equal to 2n, but you need this n greater or equal to 4 condition. Otherwise, you won't have the right inequality. Yeah. But you can specify the range. That's our n0. This number is our n0. Okay, all right. Then you raise to 6th power, so n to the 6th less than n plus 4 to the 6th less than equal to 2 to the 6th, that's 64, n to the 6th. Okay, yeah. Then, so you have the constant C1, C2, right? Yeah. 1 here. Okay. Yeah. One here, 64. Yeah. One is C1, another is C2. Okay. Yeah. Yeah. Could be this C1, that C2. No. Yeah. Okay. And N0. Yeah. So 2 methods. These 2. All right. This one, we factor that 2 square, that's 4. Okay. Out 1 square plus 2 square plus n square. Okay. Yeah. And the formula, we have it, the formula 1/6 times n plus 1, 2n plus 1. Okay. Then simplify it, 2/3 n plus 1, 2n plus 1. Okay. Yeah. 2n plus 1. All right. Yeah. The last one, answer is 4 comparisons. But you need to tell me how to use 4 comparisons. This 4, remember our lower bound of sorting formula, 5 minus 1. Okay, lower bound to give us 5 comparisons, but you're already given the first comparison result, so you can minus 1 to 1 fewer. All right, here let me show you how to use 4 comparisons to find a solution. X1, X2, we already know X1 less than X2. So we put them there as our starting state. Okay. Now, remaining two elements, X3, X4, we do comparisons with these two elements. First, let's just consider X3. Let's forget X4, okay? Forget about X4. So you need two comparisons to get it sorted, right? You need two comparisons. Two comparisons to make sure X3 join X1, X2 in an ordered array. The result must be an ordered array. Yeah, but you span that two comparisons. Okay, all right. So after the two comparisons, you will get this time three sorted elements. Can I assume these three elements is X1, X2, X3, right? I just write it for convenience. Just three elements in order. You know, there are several versions, different order, but that's not important. Okay, all right. Now, only you need to fix the last element, X4, 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 X4. All right. Now, in order to make X4 join those sorted, ordered elements, use the fastest way. Use the fastest way. The first comparison, compare with X2 first. Use the binary search way, binary search. So you know the binary search, right? Use the binary search way. Okay, so you compare X4 with X2. If X4 less than X2, you only need to do one more comparison with X1. Okay, yeah. But if X4 is greater than X2, you do not need to look at X1 anymore. You just do one comparison with X3. Okay, yeah. So this tells you you need two more comparisons to get all the elements sorted. Yeah. All the elements sorted. Yeah. For the X4, use the binary search way. That could help you reduce one comparison. You do not need to compare all of them. You only need to compare two of the three. Yeah, two of three, not all of them. Yeah, question.
So this question is like this know that it's just that how do you use logic here on question 14, which stated this known
Question.
why
In place, same logic.
is that
Oh,
last question's logic was
okay.
like, oh, it's place that means that we're not,
yeah,
and then
yeah, yeah, same logic. Yeah, but
but on here though, is it because it is comparing on the last question on this one is sorting it? That
this one I need you to give me the details. All right. So if you give me the only one number, answer 4, yeah, if I move this to, you know, if you see not the solution, if you see answer, then you use that logic You can give me 4, that's okay. Yeah. But you do not give me the detail, right? You tell me how do you apply those four comparisons. Here we require that detail. Here, but when you see the solution, you are required to provide the details. Yeah, so that's why I need you to know, not just the correct answer. What do you tell me? If I only ask you for correct answer, then I understand you refer to this question, use this way, because by the lower bound, we know 5 comparison is the best, right? Yeah, by lower bound, yeah. But that 5 comparison is the best, still one thing missing. Can you get that 5? We know 5 is the best you can, but you don't know if the 5 is achievable, right? You know, if someone gets that 5, that's the best. That's what you know. Okay, but you do not know if that number is really can be achieved. You do not know that. Okay, yeah. So when the n number a little larger, that will be an issue. Here it's not an issue because n small, n equals 4. Okay, the lower bound is achievable. When you move to 5 elements, that lower bound will become 7. 7 also achievable. Okay, we can make that. But when you increase that number, 6, 7, 8, you get lower bound. If it's achievable or not, it's unknown, still unknown. Okay, yeah. Is that lower bound achievable? Right now, it's unknown. Yeah, it looks like it's not that easy. You cannot assume lower bound is always achievable. You cannot assume that, because nobody can prove lower bound is always achievable. Nobody can prove that. It's very hard to prove it. Very hard to prove lower bound. Okay, yeah. All right, yeah. So we finish this all the solutions. Yeah, but I hope you completely understand. Yeah. I try not to make too hard for you. Yeah, just reasonably hard. Yeah. But